Chapter 8 Thunderstorms, Mid-Latitude Cyclones, and Hurricanes. Section 8.4 Mid-Latitude Cyclones. So mid-latitude cyclones, as their name suggests, form in the middle latitudes. They tend to be closer to the poles during the summer months, closer to the equator during the winter months. They're also called frontal cyclones. They're cyclonic storms, so that means that they are in the northern hemisphere. They rotate counterclockwise, and the air moves into the center of a low pressure system. Mid-latitude cyclones can be quite large. They can be up to 2,000 kilometers in diameter. The low pressure at their center can drop to as low as 970 millibars, so they can be as strong as a weak hurricane. These systems exist for about 3 to 10 days, so it's quite variable how long they last. They develop, their development is associated with the jet stream, and they usually develop in sort of the straightaway part of a bend in the jet stream. These mid-latitude cyclones represent the dynamic sort of interaction that is occurring between warm tropical air and cold polar air or Arctic air. And this is occurring along some sort of frontal zone, which we can call the polar front. In this interaction, warm air is pulled into the system. It rotates cyclonically and is lifted vertically and mixes into the upper atmosphere with colder upper air found there. Behind these mid-latitude cyclones, there's usually a downdraft of cold air from the upper atmosphere as they move past. Mid-latitude cyclones transport excess energy from the lower latitudes to the higher latitudes. So this, notice how this frontal zone is connected. We can call this the polar front. Above this front, we have cold polar Arctic air. Beneath the front is subtropical air. And the subtropical air is trying to invade into the polar air and mix within that air to sort of redistribute heat energy, excess heat energy that exists in the subtropics. Sometimes mid-latitude cyclones can stall, but they're usually not motionless. They commonly move about 50 kilometers per hour or 1,200 kilometers in a day. And their movement is generally from the west to the east. Precise movement of these weather systems can be forecasted by looking at the orientation of the jet stream in the upper troposphere. An estimate of how quickly they will move can be determined by looking at the speed of the winds behind the cold front. So the cold front is the active front moving this storm along. The warm front usually it moves at a slower speed, and the cold front is catching up to it to create a condition called occlusion. On satellite imagery, the mid-latitude cyclones look like a wave with a comma form at the center of the low. So we can see the clouds in the center of this mid-latitude cyclone. We can notice that there's clear air behind what looks to be the cold front. So cold air should have a lack of clouds. The warm air is being lifted up ahead of that cold front and creating the clouds that we see. And somewhere in those clouds would be the warm front. So this is a typical mid-latitude cyclone. They're quite common off the west coast of BC and Oregon, Washington, California in the winter months. And here we see one from January 16th, 2019. Here, this animation shows the movement of this front, and we can see how it's approaching the coast. Those white bits with blue, those represent thunderstorms at the cold front of the mid-latitude cyclone. You can run that animation again. So you can see the swirling motion, the air moving into the low and the low moving the storm closer to the west coast, and it's over the Pacific Ocean. So as I said, mid-latitude cyclone development is related to jet stream processes. Mid-latitude cyclones are generally create less damage than hurricanes, and their winds aren't as strong. At the worst, they could be as strong as a weak hurricane. They can be very disruptive during winter months, mainly because precipitation during colder, with colder temperatures, can be in the form of freezing rain or snow, which limits transportation by humans. In January 1998, a winter storm in eastern North America resulted in 20 human deaths, mainly because of falling trees on homes or cars, or billions of dollars of damage to buildings, trees, and in many cases the loss of electrical power. If freezing rain occurs on power lines, they can break, and it takes a long time, if the damage is extensive, to repair these broken power lines. So mid-latitude cyclones, the low pressure associated with them, so it is usually associated with an upward movement of air into the jet stream. In the upper atmosphere, there's divergence occurring in the air that creates a vacuum effect, pulling air from the Earth's surface. We can see the cold front and the warm front. In between the cold and warm front would be a warm sector of subtropical air. Behind the mid-latitude cyclone is usually an area in the upper atmosphere of convergence. Convergence would squeeze the air and push it downward, producing a cold high-pressure system, and these cold high-pressure systems are always associated behind a mid-latitude cyclone. So here we see there's a mid-latitude cyclone moving. It doesn't show the fronts, but we can see how it's forming in around Texas, and then moving up to Ontario and Quebec. So I'll run this animation a couple more times here. And what we've got animated here is about two days, 48 hours. So it's sped up. Here's the same animation, but now showing temperature. So watch that low at the top of Texas, how it and watch the temperatures associated with it as it moves into Ontario and Quebec. And you can see the fronts. So warm air is moving up to the west through into the east coast, associated with this storm. The following diagram shows some typical paths of mid-latitude cyclones in comparison with hurricanes. So notice the most obvious thing is that mid-latitude cyclones tend to move from west to east. Hurricanes often have an east to west direction in their movement. There's a lack of hurricanes in the southern hemisphere, in between Africa and South America. Ocean there is just too cool for them to form. You need temperatures above 26 degrees Celsius, sea surface temperatures, and likewise in the southern Pacific to the west of the west coast of South America. So this next figure describes the patterns of wind flow, surface pressure, fronts, and zones of precipitation associated with a typical mid-latitude cyclone in the northern hemisphere. So we're going to see that the winds blow counterclockwise and inwards. In the southern hemisphere, it would be the opposite, clockwise and inward. West of the low, cold air travels from the north and creates the cold front, comes from the north and creates the cold front. And this cold front extends from the low pressure center down towards the southeast direction. Southeast of the low and northward, moving warm air from the subtropics produces the warm front. So here we can see the fronts. Now, you just use your imagination that this thing is moving in a west to east direction, and the wind is swirling around it at the same time. Precipitation is associated at several locations at the low center, along the fronts, where air is being uplifted. Various types of precipitation can be produced: rain, freezing rain, hail, sleet, snow pellets, and snow. Now, it's also dependent on the season. Frozen forms of precipitation, except hail, are common with storms that occur in the winter months. Rain in the summer months. Hail is often associated with severe thunderstorms, and they like to form along or in front of the cold fronts, and that's usually in spring and summer months. So let's do a vertical cross-section through a mature mid-latitude cyclone and examine the structure of the fronts, and in particular the cold and warm front. So we're going to do a cross-section from the previous diagram that I showed you, from A to B, and look at the differences in the air masses and the types of clouds that form. So along a cold front, we mainly have cumulus and cumulonimbus clouds. So behind the cold front, the air is very cold. Ahead of it, the air is warm. With the warm front, we have clouds that include stratus, nimbostratus. The air ahead of the warm front tends to be cool in a relative sense. And in both of these cases, the precipitation is being produced by warm, moist air being lifted over both of these fronts. Okay, let's do a little weather map analysis, and what we'll find on this weather map is that there's a mid-latitude cyclone on the right-hand side of this map. So let's begin by doing just observing the data that's associated with each weather station, and those weather stations are represented by the circles. Sometimes they're filled in, indicating that we have 100% cloud cover. Sometimes they're not. 1/4 covered would be 25% cloud cover. The following data is associated with each one of these observations. Take a look at the top one in the state of Minnesota. So on the left-hand side, top number is current air temperature. The number in the middle, that 10, represents weather conditions taking place. There's a code associated with that. I'm not sure what the number is, what the number means. But the number below the 10, the 5, indicates the dew point temperature. So the 20 on the top is the current air temperature, 5 is the dew point temperature. Wind direction is from the north-northeast. The current atmospheric pressure is represented by that number 160, and what we have there is the last 3 digits of atmospheric pressure measurement to 1 decimal point. So the actual atmospheric pressure is 1016 0.0. So in the next map that I'm going to show, I've just focused on atmospheric pressure to see what the pressure patterns are, and they look something like this from the raw data. On the left-hand side of the United States is high pressure with a high located over might be Utah, the state, and in the right we have a low pressure center, and that low is surrounded by pressure values of 108 millibars on 3 different sides, and the high pressure 1024 is the relative pressure. So about 16 millibars higher over the high pressure than the low. Let's now do a temperature analysis. So let's look at temperature patterns that exist in our weather map. So what we're going to use is just that top number on the left-hand side of each weather station, and we get this type of analysis. So temperatures tend to be quite cold down the center of the United States, warmer on the East Coast, and warmer along the West Coast. And those temperatures are in Fahrenheit. So let's go back to our original map, the surface observation map, and now let's look at pressure change. Pressure change is often used to identify the location of fronts, whether or not pressure tends to change drastically around a mid-latitude cyclone. And pressure change is represented by the number below atmospheric pressure on these weather stations. So for example, if we go back to that station in Minnesota, the pressure change that's occurred in the last 3 hours is 0.0 millibars. The greatest pressure change tends to be located around where all of the filled-in weather stations are, where the ones that have 100% cloud cover, and we get the following values. So with the passage of the front, pressure should increase when the cold front passes, and ahead of the front, the pressure should be dropping. So I would think that our center of our low is located somewhere beneath the Great Lakes in the center of that part of the United States. So let's do the final analysis. Let's draw in where the fronts are and the location of the low for the mid-latitude cyclone, and it looks like this. So that was a simple sort of example of weather map analysis, locating the fronts, the center of the low, the high pressure system that exists in the Rocky Mountain states. Final topic I want to talk about is just the life cycle of a mid-latitude cyclone. This life cycle is also called cyclogenesis. And so what I'm going to show you is a whole series of slides with different stages showing the development of a mid-latitude cyclone along a stationary front where we have cold air on one side, warm air on the other, and how it progresses. And when I go through these slides, imagine it moving from west to east. So here's stage one. So a weakness develops somewhere along the stationary front, usually associated with something going on in the upper atmosphere and the jet stream, and we'll move on. So these two air masses develop some sort of weakness. In stage two, we get the development of the low, and this development accelerates. Cold air is swinging down behind, warm air is swinging behind to the left, warm air is swinging up, creating a warm front. The cold air swinging down creates a cold front. And as this system develops, the pressure at the center of the low gets drops, and the front develops more of a wave type shape. Circulation is counterclockwise. There's stage 4. In stage 5, we have the mature mid-latitude cyclone. So there's warm air in between the cold and the warm front, cool air ahead of the warm front, cold air behind the cold front, and cyclogenesis will continue. The cold front will catch up to the warm front, and we begin with occlusion occurring near the low. So that's where the cold front catches the warm front. At that occluded front, you can imagine warm air is being pushed up into the upper atmosphere. Here's stage 7. The inclusion is even greater. We have a well-developed occluded front. The stationary front is beginning to develop again. Well, let's finish off this cyclogenesis, and we'll look at stages 8, 9, and 10. In 8, we notice the low separates from the stationary front. There's no warm front or cold front no longer existing. That circular air that's moving up, we can imagine there's warm air that was once part of the warm sector between the warm and cold front is now moving into the upper atmosphere. The low slowly dissipates until it's gone, and we're back to the stationary front condition. The final slide I want to show you is just of a mid-latitude cyclone approaching the east coast, and we can see that it's got a bit of an occluded area. That green part of the line, cold front. Notice behind the cold front the air is relatively clear. Ahead of the warm front we have cloud cover. We also have cloud cover occurring in between the cold and the warm front, and this system would continue moving from west to east until the cold front totally catches up to the warm front, and the system dissipates and disappears.